Hi, Sandra. Can you hear me? See me? Or whoever's using this number from Sandra. Hello? Hi, Chuck. Can you hear me and see me? Hello?
Hey, Chris.
Hey, Chuck. Hi, Chuck. Can you hear me and see me okay?
Yep.
Okay, great. And let me try to... So I don't know, I can't remember if the link is there, if people join later or not, but I made a slight update to my PDF file. I'll share my screen, but I also put a link to it in the chat window. Does that still show up if you joined after I put it there? I can't remember for Blue Jeans.
It's there. I see it.
Okay, good. All right, and so this meeting is currently being recorded, I guess. Is that right?
Rumor has it.
A little flashing red light. I guess you chair the meeting, and should I expect that I should leave at the end of it because you guys go into some sort of closed session, or is it just an hour and then we just have a talk and questions?
As far as I am expecting, there will be no closed session after this. I'm sure the PST and the science chairs will have plenty of questions for you. Okay. That's the whole purpose. And so, yeah, I'm expecting, of order 20-ish to join the meeting today. So
okay.
I have not heard back from Steve, by the way.
Maybe he'll join this meeting. But
if he
since
does,
it's recorded, let's not discuss it here.
yeah. But I also know he's at the Aura board meeting, okay. I think today.
Hi, Eric.
Hi, Neil.
Hi.
Hi, Steve. Beth. Tony.
Hello.
Is anyone else hearing some static when Chris and Steve Ritz just said hello, or is it just me and my connection?
I heard static.
Yeah, I heard static too.
I also heard static, but just when you guys joined, but I don't hear it now. So maybe whatever it is, maybe it was just a bunch of people joining.
Yeah, I think
It's dynamic static.
Okay.
so. I suggest we give it another minute or two, and then we can get started.
Recording is.
So let me suggest that if you're not going to be actively speaking, that you mute your microphone so we don't get any strange feedback problems. I will do the same. We'll give it one more minute and then we'll start.
And just so people know, I made some minor updates to my slides. So if you did want to download them or follow along, I put a link into the chat window. There's nothing major. I just added a few people's names and found a couple sentences that I had to modify.
Chris.
And I'll go ahead and share my screen.
Yeah,
and
go
I
ahead.
heard that I heard that Brant requested this talk, so I brought my banana slug with me today.
Oh, that's terrific.
We aim to please. Okay.
All right. So, why don't we go ahead and get started? Chris Walter is joining us today, and he's going to talk to us about the status of LSST image simulations. And without any further ado, Chris, you now have the floor, but you're not yet sharing your screen. Now you are.
All right. And it's a little confusing. So do you see, what do you see? Do you see a small window, or do you see my whole screen, or does it look okay?
I see your whole screen, and you have a PowerPoint, but you haven't gone into presentation mode yet.
Interesting. Okay. Let me do it this way. So I'm not sure exactly what will happen if I go into presentation mode. Does this, well, okay, hold on. All right, let's try presentation mode. If for some reason this whole thing drops out, then somebody better call me on the phone. So, because I can't see anything else on my screen. So I'm sure one of you has my phone number. Okay, so can I go ahead and start?
Yep, you got it. Looks good.
All right. Okay, thanks. Okay, so nice to meet those of you who I haven't met before. My name is Chris Walter. I'm here at Duke University. And what I'm going to talk about today is the status of the LSST image simulations. But here's an outline of what I want to do. So first, I'm going to give you some overall context of how I think that simulations fit into the big picture, and also some comments on why the development happens the way it does. And then I'm going to tell you a little bit about the overall environment that the image simulations sit in. Because this talk, Jelko asked me to talk about the image simulations, but for those of you who aren't experts, I just wanted to show you kind of where it fits into the bigger picture. And then I'll tell you about the kind of two workhorse tools that we're using now, which is FOSIM, which I'm sure almost everyone has heard about, and MCM, which some of you maybe don't know about. And then I'm going to show you some current work that's happening and a couple of examples of where simulations are being used now. And then in the end, I'm not exactly sure what the needs of this group are and why the talk was requested, but I'll talk a little bit about how to make contributions and where I see possible LSST-wide connections to the simulations. And please just jump in and ask any questions as we go along if you have any.
So, Chris, given the nature of BlueJeans and the time delays that it has, let me suggest that if people have questions, you type them into the chat window, and when Chris is done, we can march through those questions.
Okay, that's fine too. Okay, so first of all, just a little context. So when we're simulating the survey and the images, I just want to say that the science needs and the commissioning needs are what drive the development. So there's a lot of things that you have to make choices as to what you want to simulate and what you want to make accurate. And there's a lot of choices that you could make. So for example, a lot of the development now is being driven by work that we're doing in the desk. And for studying dark energy, we really need to control systematics kind of at the 1% level and below, and we really need to understand the PSF. That's particularly important for weak lensing for a particular science case we have. So because of that, we spend a lot of time, and what we would like to do with those simulations is test our pipelines, test our algorithms to make sure we're ready when the data comes. And because of that, we really need realistically complicated simulations of things like the turbulent atmosphere, the telescoped optics, the sensors, and the readout system, because that's really what affects the PSF. So we spent, and I'll mention this later, but we spent some time thinking about these CCD sensors as three-dimensional objects and what happens when things are moving through them, because we really care about the PSF. So my point here is that, that's a particular choice. If there are other needs in the LSST-wide world that have to happen, then there are other focuses that we could choose to work on in the simulations. And the other thing I want to say in overall general context is that the simulations that we do and what we choose to try to simulate now is really closely tied to the current capabilities of the data management software. So here, this is just from some work I did, and this is a single exposure on the right and an 80 exposure coad on the left. And some things that you want to check, require, sometimes you can just make a single picture and look at it, and you can test something. But sometimes what you need to do is you actually need to make a coad. You need to put these exposures together. And the exposures, in order to do that, have to have instrumental effects removed from them. They have to be combined to reach the final depth. Sources have to be deblended. You have to measure the astrometry, should say photometry and astrometry. And so if you want to develop those algorithms, say a new astrometry algorithm on a coad, you need to be able to put them together. And what that means is that you can't put in, for example, sensor effects that DM doesn't know how to take out yet. So ISR is not complete. So for example, just picking something, if they don't know yet how to take out cosmic rays, you shouldn't put cosmic rays into your simulation, because then you won't be able to use that to do the development that you need. So this requires a tight connection between us and DM. So I spent a lot of time talking to people like Robert and Will and others to really understand what the feature set is in DM now and try to track our development along with the development of the DM project. Okay, so that was just a little bit of maybe philosophical overview of how we approach the problem. So now let me tell you a little about the environment that we work in. So by environment, I mean, what's the larger simulation stack that the image simulation sits inside of? So basically, it's got several pieces. So the first piece is, especially say on the desk side, is we have a set of cosmological simulations. So right now, that's given by the Millennium simulation, and the desk, we're currently creating a new cosmological catalog. And then there's a Milky Way model, and it's described by this paper that was worked on by Mario and Jelko, I think, and a couple others. And then we have other distribution models, and those are used to build a simulated sky, which go into this so-called CatSim database. And what's in the database now? So what's in there now are main sequence stars, red giants, blue horizontal branch stars. These variable sources are Lyrae and Cepheids, white dwarfs, eclipsing binaries, galaxies. In the galaxies, we have Circic components for bulges and disks entered separately. AGN, and a relatively recent thing is now there's moving main belt asteroids, and there's a new variability model for the main sequence stars, which is built on the Kepler light curves. And I should say that just because these things are in the database doesn't mean that they're necessarily being used. So, for example, in the desk, we're not drawing on some of these. We're only taking stars and galaxies right now. So how does that fit into the overall flow? Okay, so first of all, I just wanted to point out, with the exception of Folsom, which is mostly written in C++, all of the simulation software that I'm talking about uses a common Python 3 environment. So you can download the stack with Python 3, and it all works inside that common Python world. So here's a nice slide that I took from Lynn that she showed at a survey simulation meeting in the desk. So what we call OpSim is really a simulation of the scheduler and the simulator for the telescope. So the scheduler takes a set of proposals, which have science proposals in them, and it has as an input the observing conditions, if the moon is up, what's the seeing like, and a set of constraints, which is, how fast can the telescope move, how much can you move the filters, and it has an optimization procedure, and it tries to simulate basically what the simulator will do on the real telescope in terms of where it points over the 10-year survey. And so that's called OpSim. It's the operation simulator. And the output of that is a simulated pointing history. So basically what you have is a file, and the file tells you the day and the angles that you're pointing at and what filter that you're looking at and how bright you think the sky is, for example. All right, so for those of you who've used MAF, this is the input to the metrics framework. So when we want to use that for image simulations, instead what we do is we take this pointing history and we say, let's say this is a particular day and time and position, and we ask the CatSim catalog that has all of these things in it. I say, okay, at this day, position, and time, please tell me, and in this focal view, in this field of view, please tell me what galaxies you see, what stars are there, and it returns a list of those objects at that time and position from the CatSim catalog. So that's the overview of how everything fits in. So this is the workflow summarized. So first of all, we take the cosmological simulations or other models, and we load them into this CatSim database along with this Milky Way model. And then driven by the OpSim pointing, so OpSim is already run, the database is queried, and we produce what's called an instance catalog. And those instance catalogs are used as the input for the image simulations. And the instance catalogs can be created and read in a human-readable format, and they can even be handmade. So I'm going to show you a nice example later in the talk of some people who did a little test thing themselves where they just put these things together by hand. Or you can make you can drive it in kind of a more machine way. So then we run the image simulations, and what comes out is something basically that looks like what comes out of the telescope. And then we take that output and we can process it by either the static or transient pipelines that are in the data management stack. And this produces a set of output data products. And so in addition to processed images and tables, so we have the calibrated exposures, but we also have the coads. We extract catalogs from the outputs, and then from those catalogs we can also do science. So let me tell you a little bit more about this instance catalog. So the instance catalog, which remember is the thing which is the basically list of items that you want to observe, is based on the instance catalog format. Both tools are based on the instance catalog format from the Folsom tool. So I have a link here. If you click on this link, you can see what all of the terms are. There are a couple differences between Folsom and MCM on what goes in here, and they have to do with proper motion, the way proper motion is handled, and which sources are currently supported between the tools. In other words, can you have a 2D SURSIC or 3D SURSIC or a moving object supported? So a couple minor differences, but basically the same. So what's in one of these instance catalogs? So I don't know how well you can read this, but the first thing is a set of things which describe basically the seeing and where the telescope is pointing and what the day is and where the moon is in the sky. So and where the sun is and how long you're doing the exposure for. So this is sort of parameters that tell you about the environment. And then what you have is a list of objects. So you see each one of these starts with objects. This first thing is basically an ID. And then each of these things tells you where that object is located, or RA and DEC, what the set of the object is. If you can read this, you see it says like star set, and the bottom one here says galaxy SED, and it has some file that it reads, what the extinction is from dust, and if there's any proper motion, for example. Okay, so you can actually write this by hand if you want to do some tests, or we have software which can pull this and create these straight from the CatSim catalogs. All right, so what are the main image simulation tools that we use? So remember, we've made one of these things now, and then this is the input for one of the image simulation tools. So how do we actually use it? So there's sort of two main ones now. So the first one is probably well known. It's called FOSIM. So this is a well-known LSST project. We've been using it for a long time, and it utilizes photon by photon ray tracing in the atmosphere, the optics, and in the silicon model. And it can, so in other words, but photon by photon, in principle, one can track that photon as it bounces around through the atmosphere, through the optics, and into the silicon. In practice, for computational reasons, usually the photons are bunched up in groups, at least until they get to the telescope. But in principle, you could do it exactly photon by photon. It contains an LSST electronics readout module, so the output that comes out of it should look like the amplifier output that comes off of our sensors. And because of the way this works, it results in an emergent PSF. So in other words, you don't tell it, I want a PSF which is a Kolmogorov spectrum convolved with instrumental Gaussian. It just comes out of it based on the first principle physics parameters you put in. It contains its own self-contained consistent sky model, and this is really a standalone program. So that means that you can check it out and you could run it on your laptop, or you could run it at some bigger system, and it doesn't rely on having the rest of the LSST software around at all. You could just use it. Okay, so the other tool is called MCM, and so this is an LSST GalSim-based simulator. So GalSim is used as a library. So those of you who don't know what GalSim is, it's an open source software that's been used for some community challenges, especially for weak lensing, but it has sort of a generic image drawing engine with convolution and things and noise built into it. So basically, MCM, which I was the original author for, is a set of scripts, and it's a program which utilizes the project build tools, LSST spectral emission distributions, our official LSST sky model, which is the European Southern Observatory sky model, with a twilight model that was added by Peter Yoakum, and LSST electronics readout. So currently, this uses an explicit PSF. So we tell it, I want you to make something that looks like a Kolmogorov PSF involved with instrumental effects. So that's fast. Upcoming features include atmospheric ray tracing and a silicon model tuned on the LSST sensor property. So I'll say more about that in a minute. So the main contacts for these programs are John Peterson for FOSIM. MCM, the main contact would be me, or Jim Chang, who is a scientist at SLAC and is also one of the main developers of the program. So I should mention one sort of historical thing. If you go back and you look at very old LSST slides, you'll sometimes see MCM written down, and it has a different meaning there, actually. It used to refer to everything in the simulation stack all put together. And so when I first started writing MCM, I needed kind of a placeholder, and I didn't know a good name, so I wrote it down, and then as these things happened, it sort of stuck. So it has a slightly different meaning now. So let me give you an overview of FOSIM. So this URL at the top is the official site where you can go, and so this is where you can download it, and you can find documentation, and you can also issue tickets for bugs or things if you find them for the FOSIM team. So it's a set of photon Monte Carlo codes, and basically what it's used is to calculate the physics of the atmosphere and the telescope and the camera, and the goal is to simulate realistic optical and near-infrared astronomical images. So what it can do is it can read the instance catalogs that I just showed you before, and then it can propagate the sources photon by photon through a realistically modeled turbulent atmosphere, and then it can propagate those photons through an optical model. So this is like Zmax. You can, in fact, the files that it uses to describe the optics are basically Zmax files. So you describe lenses and mirrors. And then it can propagate bunches of photons into a sensor model. And what that sensor model is it's a set of static potentials plus a dynamic dipole potential, which is based on how much charge is already in the pixel. And then it pre-calculates the kicks on the electrons as they're coming into the sensor based on adding those two things together and doing it iteratively. And there's really a large list of sensor effects that you can also turn on that John has put into the program. Then you can write out the resulting full focal plane images with the proper LSST camera and chip geometry, including the typical readout chain. So as I already mentioned, FOSIM is a standalone program. So that means you can easily run it on laptops to enterprise systems, and you don't have to install any other software to use it. In fact, it has only a few dependencies, and if you want, it can install its own version of them in its own directory. So a little more details on FOSIM. So FOSIM's under continuous development by a team at Purdue that's led by John Peterson, who's a faculty member there. There are some relatively recent control modes that were designed along with the system engineering team, particularly with Bo Jin, that allow the optics to be perturbed with the degrees of freedom of the adaptive optics system. active optic system. So in other words, the active optic system, I think, has 35 degrees of freedom or something. So you can move one of those like we will do during the real running, and you can see what the effect is on the output. And I'll talk a little bit later about how that's being used. So the current released version is version 3.6. There's a beta version that's now available to a few people, and mostly people in the desk, and they're testing modifications to this. And the modifications are focused on performance and threading capabilities, and specifically, that's to allow it to run efficiently in a high-performance computing environment, which is where we do a lot of our computing. All right, so now let me give you an overview of MCM. So this URL at the top, which is a GitHub URL, is where you can find the code and the issue tracker. It's all open. You can find everything there. So this shows you the pieces of this program. So basically, MCM takes as an input all project-wide LSST pieces of information that we have that describe the instruments and what we think the inputs will look like. So it uses instance catalogs, which are actually the same ones which are used by Folsom, but they're more up to date. We have, it uses the format of the instance catalogs. It uses the SEDs for LSST. Those SEDs eventually usually wind up in Folsom a little bit later. We use the site information that we have for LSST, and we have a model of the sky. That's all input into MCM. And I want to emphasize that unlike Folsom, MCM is not a standalone tool. It's developed in and requires the LSST software environment. So it uses the LSST software build system. It requires, whenever we can, we try to use the LSST libraries for its use. So it calls the LSST sky model. It calls the LSST camera model, for example. So then what happens is there's a piece of software, which is a GalSim interface code. This is part of the LSST Sims directory. This is written by Scott Daniels at Washington. And then that calls GalSim, and GalSim is basically used as the image renderer. That's the basic overview. So here's some of the same things in words. So MCM is a Python program. It uses the LSST project tools and inputs. There's some double word here. It prepares inputs and driving commands to GalSim. For those of you who don't know, GalSim is an LSST open source. Okay, I tried to correct this text, but obviously my cut and paste skills were not completely up to par here. So there's not supposed to be LSST here. So MCM is an LSST program. GalSim is an open source software for simulating images of astronomical objects in a variety of ways. So doing things this way gives a very clean separation between the GalSim and the MCM development. So if you look back here, we can do all the development we need here on MCM for things that are specific to LSST, but things that are generic about how we track photons to the atmosphere, or how we draw images, or how we can evolve other images, that can happen in the GalSim code. So LSST specific features, which are needed for our environment of simulations, can be developed in MCM, and whenever possible, MCM leverages the LSST project models and libraries. So there are some similarities and differences to Folsom because of this. So once again, it reads instance catalogs. It also propagates sources through a realistically modeled turbulent atmosphere, but it has a few different ways of doing it. So what's been done recently, we can do a full diffractive fast Fourier transform calculation through a turbulent atmosphere. That's very slow, but it's actually accurate in that it has all the diffractive effects happening. We can put a fast parametrized PSF in, so we can know that the result of that is a Kolmogorov spectrum from the sky convolved with some sort of other instrumental spectrum. So we can just tell it when the light shows up at this source on the sensor, use that PSF. And there's also a new emergent ray trace code. So basically, like what's done in Folsom, where we can trace the photons, photon by photon, through the atmosphere, that Josh Myers, who was at Stanford but is now part of the project DM team, is working on, and this will be available soon. So actually, the most useful thing about this is that we can do the full calculation, which is extremely slow, and then we can compare it with this ray trace code, which is really an approximation, because you have to make some approximations to get the diffraction in, so we can see how well that works. So we can further perturb the wavefront as it passes the LSST pupil, but unlike Folsom, there is really currently no optical ray tracing. So one thing that's happening, which I'll mention later, which is under development, is making sort of a phase screen which represents a modification to the phases which are coming in, which represents the aberrated optics from the active optic system that's under development. And there's long-term work on optical ray tracing, which has begun. So then we can propagate individual photons into a physics-based LSST-specific sensor model. So, there's another goal here, which is a goal which we've had for a long time, which is to produce a validated sensor model. And what I mean by validated is it's a model where we simulate things, but we tie it to a set of measurements which were actually made in the lab, so we can actually see that we're doing the right thing. This is particularly important for understanding these sensor effects that are important for the PSF. So we have laboratory readouts at Brookhaven and Davis and SLAC and France, and so we have a set of tests that we do, and we want to make sure that we can do those tests and see that we can reproduce them. The other thing that we're doing is we're actually physically characterizing LSST sensors. So there are a couple of dead sensors, and we've taken those sensors and actually used scanning electron microscopy to look at the substructure in them and measure their properties, and then put that into our model. So there's a researcher at Davis named Craig Lage, and he's written a separate, detailed, and relatively slow electrostatic solver that was been built for this purposes. It's very detailed. It's very impressive. You can have him come give you a talk about it sometime. We can even do things like change the voltages and see how things react. But that's too slow to put into MCM. So what we've done instead is GalSim has a fast interpolator that can basically use the output of this model for simulating the sensor effects. And I'll show you later how that works. And then we can write out the resulting full focal plane images with the proper LSST camera and chip geometry, including the readout chain, just like in Folsom. Okay, now I mentioned the sensor and the readout effects a couple times, and there's actually an enormous number of them. And so, you have to ask yourself which one of these, first of all, which are really needed, and which can you be used now? Some of these, if we turned on, we would have no way to deal with in DM, so it wouldn't be a good idea to turn them on yet. And then the other question is, how can we actually validate them? So I'm not going to go through all of these. I think I made this list, and almost all or all of these are actually possible to turn on in Folsom. Most, but not all, are possible to turn on in MCM now. MCM hasn't been around for as long. So, for example, we can't turn cosmic rays on in MCM because we haven't needed them yet. But let me give you an example of a few of these. And the way I want to give you the example is not just to pick a couple of random ones, but to show you kind of three categories of types of sensor effects and how they can actually be important. So the first one is one which I've worked on a little bit, so it's a little dear to my heart, and it's called the brighter fatter effect. And you've probably heard those words floating around in LSST. And that's basically, for those of you who've taught freshman physics, it's just space charge. So it's nice because you start thinking of these CCDs like really three-dimensional objects. And when the next photon gets converted to an electron and it starts coming in, if there's already a bunch of charge which is there in the pixel, it feels the field from this charge that's already there, and it deflects it, and it can wind up in the other pixel. So the effect of this is when there's nothing in there, it starts building up in this pixel, but as it starts getting bigger and bigger, the spot gets wider. So that's why it's called the brighter fatter effect. It's particularly relevant for PSFs because usually the way we measure PSFs is by measuring bright stars. So if you use that PSF and then you go and deconvolve a galaxy, which is very dim, you'll get the wrong answer. And the special thing about this effect, though, is that so it changes Poisson statistics also. So if you look at something that's flat, you won't see the normal sort of variation and correlations over the sensor. But the important thing about this is it's a dynamic effect. It's not static. So as you collect more and more charge, this effect changes. So it's not a simple convolution. So how we actually correct for this in DM is actually a non-trivial problem. And you want to be very careful because you don't want to build something which is just a correction of what you put into your simulation, because that looks like you can correct for it perfectly, but in real life, you might not be doing as good a job. So we need to try to do something which is physically motivated in the simulation, and then we have some more heuristic techniques which have been developed for correction. Okay, so this is a dynamic effect. Now, so this happens depending on the level. Now, on the other hand, some of you might know that when the silicon bowls are grown, they're grown over days, and ambient conditions like temperature and humidity can cause doping variations. And just like a transistor is an NP junction, and the difference between the N and P gives you an electric field, the difference between N and less N also can give you sort of a junction, can give you an electric field. And so the effect of that is that you get lateral electric fields, and because of the way the boule grows, you sort of get this thing that looks like a tree ring. And in fact, once people understood this, you can actually look at sensors on a focal plane and see how they're cut up and see how they were cut out of the original piece of silicon boule. So this is a static effect. This is completely frozen into the silicon. So in principle, if you can measure this ahead of time, you can actually go in and you could treat this, like, for example, as a WCS correction. You can think of it as kind of a conformal mapping between stretching something on the top of the sensor to the bottom of the sensor. So this is something which is, if you can characterize it, is easy to correct after the fact. And there are more sensor effects, and this is an interesting one. I don't know how well this is going to show up on the screen, but this is from fringing. And so once again, for those of you who have taught freshman physics, you know you've taught the interference effect before. This is similar to that, right? Because as you go through the silicon, the signal is being depleted exponentially, and then it bounces back up. That's the interference effect that you normally have, but it's not the light that's coming out which is interfering. It's the light that's inside of the silicon which is converting into an electron. But so you sort of get this pattern. But the interesting thing is, if you look inside this pattern, I don't know how well you can see it, you can see there's actually more than one frequency. So like if you look here carefully, you can see there's a big set of fringes, but then there's a smaller set of fringes here too. And this is the reason that's true, is because there's several layers inside of this thing, and the layers have different thicknesses, and they're sort of oriented in different ways. So this is a multi-layer thickness effect. Now, this is a static sensor property, so you might think like, oh, in principle, it's easy to take care of this sort of thing. But the reason this is interesting is it can actually be dynamic, because, you know, for example, as you go through the night, you have OH lines in the atmosphere, which are, you know, sort of monochromatic lines, which can cause this kind of fringing, but that changes throughout the night. And as you know, thinking about just simple thin film interference, where the interference shows up depends on the frequency. So exactly where the fringing shows up is something which depends on what's happening in the sky. And so actually the people who did the monocam tests, where they took an LSST sensor and brought it out to the US Naval Observatory several months ago, are trying to see if they can see this effect. So here's three effects, and I just think it's interesting that they fall into different classes. So some are dynamic, some are static, but they're still dynamic. Some of them are instrumental. You have to think differently about all of these different cases. So I mentioned this electrostatic solver, so I think it's very interesting and impressive. So let me just mention it. So this is done by Craig Lage at Davis, and basically what he's done is he's built a full three-dimensional Poisson solver. And so you set up the external conditions, and you say what charges are already there, and then you solve Poisson's equation, and you do that over and over again. And now he can use this to reproduce the brighter fatter effect, diffusion, saturation, voltage dependencies. It's very impressive. And there were some things that he couldn't make work quite right. So as I mentioned, what they did was they took this is a ITL sensor, I think, and that stopped working, and they cut it open and they put it in a scanning electron microscope so they could actually see where the oxide layers and things were and try to measure the doping properties. So then they were able to put that back into the model, and then we saw it started behaving the way that we were actually seeing in the lab. So that's great, but it's very slow. We can't actually do that on a star-by-star basis or something when we're running the simulation. So instead, what is done is they run a slow simulation, say in a 9x9 set of pixels like this, and they start putting the electrons in the center. And the effect is, say for example, in brighter fatter, as it gets brighter, some of the electrons go into these resulting pixels around, which effectively is as if you were making this pixel larger and this pixel smaller. So what he does instead is he basically looks at the edge of this pixel and how it's been distorted. He parameterizes that as a surface, and then as a function of the amount of charge, he keeps track of how that surface moves. And then there's an interpolator that Galsam knows about that can read a file in that tells you how to reproduce this shape, and basically does superposition to reproduce the effects of this simulator in a fast way. And so this is something which we're planning on using for MCM, and it will be the basis of our validated sensor model. So then this is simulating the sensor. There's a different kind of model that's in Folsom. So then of course you want to take what's in the sensor and you want to read it out. And there's actually two kinds of outputs that you should know about. So the first one, these are pictures of sensors, and notice that there are 16 amplifier segments here. So each amplifier is read out separately. So in the real experiment, what you have to do is you have to read out the data from this amplifier, and then you have to, match the gain and do all the ISR corrections. So there's two modes. So the first thing you can do is you can read out something called an E-image mode. And what that is you should think of this like it's an image with perfect instrument signature removal applied. So we don't go through the amplifiers, we just write out basically what the electron level is in the full sensor, 4,000 by 4,000 pixels. The other mode is both codes can create realistic output, which basically gives you output on an amplifier by amplifier basis, which is what it looks like coming out of the real camera eventually and out of our test stands at SLAC and Brookhaven now. And so then we can actually take that and we can run it through the actual DM process CCD scripts to see how they work. All right, so now I'm going to switch gears and I'm going to tell you about a couple of efforts where the simulations are really being used. The first one is quite a large effort, and it's what we're doing inside of the Dark Energy Science Collaboration. And this is a set of data challenges. And so just to give you an idea of what's going on, this is a picture which is from an internal planning document in the desk. And we're planning 3 data challenges. The first data challenge basically just ended. We're in the process of planning the second one. And the idea here is to make a set of ever increasingly realistic and larger data sets that we can use to test our pipelines, develop new algorithms, and compare with precursor data. So we started DC1. So here you see DC1, DC2, and DC3. These are the 3 data challenges. Here's the years. 16, 17, 18, and then we're trying to think about how that matches with the commissioning that will happen in the commissioning camera and the science verification analysis and the commissioning period, and then when LSST's real camera goes in, what that commissioning period will look like, so that we have the data that we need to do the test that we have before that data shows up. So we started DC1 with 40 square degrees. DC2 is under development now and will be 300 square degrees. We are currently evaluating long-term plans for DC3, but likely it's going to be matched in some way to the commissioning camera and or planned mini surveys. And so for DC1, we also had something called Twinkles, which was a single sensor in 6 bands, and it was oversampled in time-dependent sources. So lensed AGNs and supernova. It's called Twinkles because things were twinkling, and we put way more in there than it would really be there so that we could test our algorithms. So here, let me show you what the survey parameters were for DC1, and then I'll tell you what we're going to do for DC2. So for DC1, we had 40 square degrees, but it was really only in 1 band. It was only in the R band. And the cadence was the Y-fat steep OpSim cadence. The sky model was either FOSIM model, so we ran both FOSIM and MCM, or this project model that comes from the European Southern Observatory, but it wasn't varying on the sky. It was just fixed to whatever the central pointing was. And then we were really interested, and I'll show you something about this later, about studying something about the dithering strategies. So in MCM, FOSIM was, so we designed a dithering strategy, which had both translational dithers and extra rotational dithers. And FOSIM had both of them, and in MCM, we ran 1 set with only natural sky rotation and 1 set with extra rotation that happened after every filter change. So this resulted, depending on the dithering, in between 8 to 2,400 visits on the sky. And for reading out the sensors, we only had E images. We didn't try making any amplifier outputs. And to start, we had no brighter, fatter, or tree rings or any of those effects because DM didn't know how to deal with them. So we basically produced 3 data sets. We made a FOSIM data set, and then we made 2 MCIM data sets, 1 dithered and non-dithered. And then one thing we were those of us who weren't experts were surprised to find out is that it takes about 5 terabytes of image data, but after you run DM on them, each of these data sets were 75 terabytes that were sitting on the disk. So that was large. So let me show you some interesting pictures of what this might look like. So here I took some of the output that came from DC1, and I ran the DM Butler on it. And on the left, you see 1 30-second exposure. These purple masks are where it thinks detected sources are. And then on the right is what happens after you co-add 180 exposures together. So this is kind of what things would look like in one band in LSST. And if you look at this blow up here on the top, you can see the green where it finds all the different sources. So this gives you an idea of like the density of sources that you would get. This is the Twinkles Folsom output. This is not a black square, so I suggest that you look on this link, or if you look really, really closely, you'll see this is 6 bands, so you'll see colors and you'll see lots of galaxies in there. And this required us to upgrade our CATSIM capabilities to be able to handle time-dependent supernova and lensed AGN, and one thing we're adding soon will be lensed supernova. Okay, so the thing that we're planning, and so we're using that DC1 to do a bunch of studies now, but right now what's happening in the desk is that we're thinking about DC2. So this should increase the size, the bands, and the realism. So this has a new cosmological simulation. It'll be 300 square degrees, 6 filters, dithered visit patterns, transient sources with an embedded Twinkles field and probably other oversampled deep drilling fields. We will turn the basic sensor effects on, and we will read out the amplifiers. And so this is how in the 10-year survey, how many visits you expect to see in every band for particular pointing. So comparing 300 to 40 square degrees and going to 6 bands, this means it'll be about 33 times more data than we did in DC1. And so this is kind of a straw man design, which we gave to the desk analysis groups to get suggested changes from them. And this is just a small part of the wish list that we got back from our analysis. So reasonably complex SEDs, lensed supernova, galaxy models beyond simple co-elliptical models, dust models and different dust models in the Milky Way, intracluster light, trying to use at least partial rolling cadences. We were planning on just making one 10-year output. What about year 1 or year 3 coads and a possible transient alert stream? And now those of us working on this are going through these requests to refine our plan and also incorporate project and commissioning needs as well. So I just want to mention that this kind of challenge takes non-trivial resources. So DC1 took on the order to 20 to 30 million CPU hours at NERSC, which is the DOE Computing Center, and the majority of that time was used by FOSIM. We produced 3 75 terabyte output data sets, and part of this exercise was just for us to learn how to handle this much data and these requirements and understand what's necessary to store and move this kind of data around. So now what I want to do is I want to show you a very different kind of example. This is a very small scale example. And this was working to simulate resolved and unresolved stellar populations. So these 4 people were interested in dark matter, and they had a 1-day mini hack because local stellar populations can be important tracers for dark matter. And what they wanted to do was to see if they could simulate unresolved light. This is also important for things like simulating intracluster light, which is unresolved. And so this is an example. So they managed to do this in 1 day. This was done with MCM. So this is an example of a dwarf galaxy. So they were trying to simulate a dwarf galaxy. And if you click on this link, you can see how they did it and more pictures. And here's a picture of a stellar stream that they made. And here you see the unresolved light and the stars. And basically what they did was they just made one of those instance catalogs by hand, but they made really, really wide Gaussian diffuse objects, which they just put into the instance catalog and just laid them along in a line to get this, or they just put a big one here. So that was done by just a few people. So one of the things that's happening now is that we're using simulations for commissioning. We're thinking about how to use the simulations for commissioning. So we'd like to target the simulations that we're doing to help with the commissioning that's going to happen in our planning and once we're on the mountain. So Bo Shin in the system engineering group is already using FOSIM to take an exposure, read out the wavefront sensors, adjust the active optics, run another exposure, and repeat. So, and we're trying to think about how we could use FOSIM or maybe a fast mode in MCM to simulate full nights of active optics control. The Data Challenge 3 in DESK was originally planned to focus on ComCam-sized LSST surveys, but now we're thinking we probably should really focus on the actual commissioning camera and the mini surveys. We are considering extra studies we could do for commissioning in the DC2 era, so this active optics is one of them. And we also want to design the analysis scripts and tools that we could use on the mountain during the commissioning now. We don't want to be writing that stuff then. So we can mock up that with targeted simulation runs and then get the stuff ready so that it's ready to go. Simulations will be particularly powerful if we can pair them now with precursor data processed with our same tools. Because of time, I think I'm going to skip this, but this is just an example of trying to mock up the effect of the active optics as a sum of Zernike terms to make an aberrated optics screen. So that's an interesting subject. If you want, ask me about it. But I think I'll skip it. But this is another example I thought people in this group might be interested in. So one of the things that we can use these for is to study different dithering strategies. So we of course do that already with things like math, but especially for things like weak lensing, we are interested in what's the impact on our systematics for patterns that might be, for example, frozen into our focal plane because the sensors aren't really symmetric. And so one of Eric Goiser's students, Hamna Amlin, I think Eric's actually on the line, she did a really nice job of designing a dithering strategy that we used in DC1. And I don't know how well Blue Jeans is going to work, but I'm running a movie. And what you can see is it was designed to make one rotation after every filter change and have a hexagonal dither translational pattern, and then move around and then remove any sensors which aren't actually needed so that we can save processing time. And so the result of this was a very nice four field of view data set with uniform depth. And then we can compare this against the data set that we made with only natural sky rotation and see if there are any differences. Hopefully that movie worked for you. If not, I'm sorry, but you can hopefully get the idea. Okay, and then this is just some work that I did. I just picked some random things. This is some data that I used from the catalog. I just wanted to show you that in principle, we can use this to study effects to make the scripts ready, for example, when we're on the mountain. So this is interesting because what we did was, we have the truth catalog. So I matched that catalog to what came out of our catalogs. And I did things like I checked the astrometry and the photometry. And this is the reconstructed astrometry versus the true astrometry. And you can see there's a 20 millisecond offset. So this was us discovering something the DM already knew, which was that there's no proper motion in the DM code now for measurement. So it's actually quite sensitive. So we can mock up things like that if things were off to see how different they are. Here's something which is basically showing you the PSF magnitude versus the difference in the truth, and you see there's some saturation here which isn't supposed to be happening, and there's some smaller population that isn't saturated. It turns out those are all on the outside. So I think this is an effect somehow of how the co-addition is happening and how the interpolation is happening for very bright stars. So we can study that and see how things are working, the kind of thing we can do. And then finally, we can do comparisons against precursor data. And one really nice thing is the Hyper Supreme Cam is using the same software as us, basically. So this is a nice paper written by Jim Bosch, considering their pipeline. This is showing the star-galaxy separation, which is basically created by comparing two photometry algorithms, PSF magnitude and the C model magnitude. And here they've used HST data to get the truth information. Here I've done the same thing in the DC1 data set using our truth catalog to try to see how these performances, how the performance looks against real data, so we can try to see how realistic the simulations are. Okay, so finishing up, I just wanted to mention some thoughts on contributions and connections. So you might notice this is a colorful slide, but the colors actually have meanings that they correspond to different communities inside of LSST, inside the LSST overall family. So there's no large set of image data being produced by the project for either continuous integration or for DM or for science studies now. All the stuff I showed you is basically being produced by the desk. So in the desk, we are considering making our data sets publicly available as a data release after we have done things like written papers with them. That would be available to everybody, including people in LSST. Staging the larger data sets, like for DC2 or DC3, is actually probably going to be an issue for us. So perhaps this is something the project might be interested in doing to test infrastructure. That data could then be available to the larger LSST community. And smaller subsets might be available now, especially for continuous integration in the data management team. And I talked to Frosty about this. She's quite interested in it. The project could also produce its own targeted data sets. So we could decide that the different science collaborations need things and the project could do it. And the thing I kind of want to leave you with is that for those of us who are working on simulations, I don't think the needs outside of the desk are really well understood. So we don't really know what other people want or need, or if they need anything. So if you would like to contribute, contributions to FOSSIM should happen through John Peterson. You should start at the Big Bucket site. And although hosted on the desk, MCM is an open source project on GitHub, and we really welcome others in LSST who would like to make a contribution, so you can get in touch with me. If you go to the website there, you'll find a list of issues, including things where we need help. And if there was something that somebody from another science collaboration needed, like, I don't know, moving objects, that's not something which is in MCM now, but if you had a student or something who wanted to work on it, they could work on making that kind of contribution. So concluding, I'd say there's a large ecosystem of tools that work together in the simulation tool chain. For the image simulations themselves, the FOSIM and MCM are the main two workhorses. FOSIM's a standalone program. MCM's a tool that uses GALSIM as a library, but it's really embedded in the LSST system libraries and tools, so you really have to have all the LSST software installed to use it. And DESK is really making heavy use of simulations now, and we're thinking about how to leverage them for the commissioning, both in the DESK and in the system engineering group. And that's it.
Great, thank you, Chris. Excellent presentation. And so, and to those that put in questions into the comment, the chat area, thank you for that. And so we have about just shy of 10 minutes, so we'll have to be quick on this. So real quickly, Chris, I had a couple questions right up front. Is CatSim something that you download and install yourself locally, or is that a remote service that how do you use it?
It's a remote service that sits at University of Washington, and you query it. It's basically an SQL database.
Okay. And my next question is probably one that we don't have time to fully answer, and that maybe we can follow up later. But I was wondering if you had a thought on when was the most appropriate time to use FOSIM versus MCM. I mean, you presented both tools, right? So when would you use one?
There are certain things that you can only do with FOSIM, especially, for example, related to the way the active optics and things work now. I think right now I'm interested in comparing them and when and how we use FOSIM and MCM for some things that are fast. I mean, in the desk right now, MCM is much faster, so we may need to use it for larger areas. It's also a little. The other thing about MCM is it allows you to override things. If you want to put in just some sky brightness that you have, you can do that. You can't do that in FOSIM because it has a sort of a self-consistent model. So they both have appropriate uses, and it's a relatively complicated question about why they're being developed the way they are and when you should use one or the other. So we could talk about that later, but probably it would be too easy to use up all the time if we continue to talk about it now.
Right. So, okay, related to FOSIM, Tom Loreto was asking, is there a paper on FOSIM that describes the details of the model?
Yes, and if you go to that website, do you guys still see my screen?
Yeah.
So this page, this FOSIM overview page, has this Bitbucket wiki home. So there are links there that have descriptions of the models in them.
Great. Thank you. Let's see, I'll skip over my question because you and I can catch up on that offline. Question from Michael about the nature of the tree rings and how these are corrected for. Are they flat fielded out? And the figure that you show of these tree rings, is that from real data? Is that simulations?
Okay, that's a good question. If I remember, because I copied this from a previous slide. I think this is from. Okay, I think this is actually a picture which is done. Okay, I don't really remember for sure. I think it's real data, but not from one of our sensors.
Right. Is it a response to uniform illumination? Or is it a map of physical shape?
This one is actually not a map of readout. I think this is a map of a type of illumination. Okay. But I had another slide which was a map of readout from DECCAM, but that is harder to see, and I thought you guys might not be able to see it so easily on a PowerPoint slide.
But does it flat field out?
You don't want to.
I think you can't just flat field it out because it shifts stuff into the other pixels.
There are astrometric distortions. You don't want to just flat field it out.
And so, in fact, a lot of people used to think that this was a QE effect, but we realize now it's not. So you can't just flat field it out. But it can be handled, for example, by a WCS. That can be done. So I can't exactly remember what the plan now is. You should ask Robert, who I think is not there today, about what the plan is in DM currently. But there's several ways.
As Chris says, it's pool dependent, and so far we see it at a very, very, very low level relative to, say, decam.
Right. I should have said that. Thank you, Steve.
All right. From Tom Laredo on slide 15, brighter, fatter. What was meant by the change in Poisson statistics?
Oh, so imagine making a flat field, right? So what happens normally if the light is just coming down is that you have Poisson statistics as to how you fill up a pixel, right? With Poisson statistics, it's just a counting number. But because of the way the brighter fatter effect works, if there's a little more charge in one pixel than the one next to it, instead of showing up in that pixel, you might wind up in the next pixel. So it generates correlations between the neighboring pixels. So if you just look in a single pixel and you look at the error on it, the square root of the mean, it won't be a straight line. So if you look at the correlation coefficient across a flat field, you'll see that it's actually correlated, and the slope of that correlation is tied to this brighter fatter effect. Did that explain it well enough?
Yeah, I think that, at least for me, it did.
Yep, thanks.
Next one is from, I'm going to mispronounce the name, Aparajita Verma. Of the SIMS tables models listed on slide 5, what was included in DC1 and foreseen for DC2?
Okay, so in DC1, galaxies, I think AGN, and main sequence stars. I can't remember. I think there's no Cepheids or RR Lyrae, and I don't know whether the red giant and blue horizontal branch stars are in there. I'd have to go back and look or ask Scott. For DC2, basically the same thing. Yeah, I mean, we're not, for example, putting in moving objects. There are supernovae that are in there, and we'll also have lensed supernovae, but we're not putting in things like white dwarfs and eclipsing binaries. It's not part of the plan currently.
All right, and lastly, there's a question on the ease and difficulty of someone adding in moving objects to simulated image from FOSIM, and then there's been quite a follow-on discussion about that, and I can't quite figure out who that is, but.
Okay, FOSIM, you should be able to already do it. FOSIM, there is a type of moving object type already. In MCM, we don't have that. We haven't implemented that type of object in the instance catalog, although stars can have proper motion, so you could think about it. So I'm pretty sure in FOSIM you can already just do it. Not positive, but I think that's the case. In MCM, somebody would have to do the work to add it, or think about if there's a hack that you could use to use the tools that we already have using proper motion.
So when you create an instance catalog out of CatSim, the RA deck of the instance does or does not have proper motion on it?
It's handled differently in FOSIM and MCM. In MCM, we wrote it in a way that we thought was a little easier to understand, just so that your brain doesn't melt. So basically, what happens is you write a program which writes the instance catalog. It writes out the RA deck, and there's an extra entry in the line, which is the proper motion. And then when MCM reads that in, it applies the proper motion based on the date to figure out where it should be in the image. In FOSIM, I'm trying to remember exactly how it works. There's no separate line for the proper motion, but it's calculated. Since there's only 1 minute left, I'd have to look. But basically, in principle, it will work properly. Exactly how you give it the inputs is a little different. In the MCM case, you just basically give it the 2 proper motion numbers, and it will apply it after looking at the date when it makes that image.
All right.
But what is true is that DM doesn't know how to handle that yet. So if you do that like we did, then you'll notice these astrometric shifts. That's something. There's an issue. They just haven't gotten around to adding it.
All right. Well, again, Chris, thank you very much. There's been some good feedback here, and I think this is what people were after. And I appreciate you taking your time today and giving us this summary. And we're now T-minus 5 seconds, but if there's any last questions or comments, why don't we give it a moment here, and then we'll sign off. Any other comments? Hearing none. Again, thanks a lot, Chris. Appreciate
Okay,
it.
I'll try to read through the chat window, and if there's anything that's obvious and simple, maybe I'll send an email to Chuck and he can forward it on. Otherwise, feel free to get in touch with me if you have any questions. Right. Nice meeting everybody.
Chris, very helpful.
Thank you.
Really great. Bye-bye.
Bye-bye.
Bye for now.